Okay, so we are very happy you joined us for this webinar today. Thank you all. It was organized by the French Competence Center, CCFR, and INRIA Academy. So it will be hosted today by me, Marie, and Guillaume Barbier, also from the CCFR. And this will be a webinar on SOFA, the powerful open source framework revolutionizing biomechanics, robotics, and medical simulation. So today you will assist to an introduction to this SOFA open source project and its ecosystem. You'll see real-world applications, hands-on tutorials, and how to design products and collaborate with the SOFA community. So all this will be presented by Hugo Talbot, who is SOFA project coordinator since 2016. So please enjoy this webinar. If you have any question, you can use the Q&A section at the bottom right of your screen, and every question will be answered, so don't hesitate. So now I leave the floor to Hugo.
Thank you very much for the introduction. Good afternoon, everyone. So as Marie just said, do not hesitate to use as much as you want the like Q&A area to post questions. The chat can be used for chatting, but yeah, do not hesitate to use the Q&A area for posting all your questions. So yeah, the topic of today will be about SOFA, which is an open source framework for simulation. And so I will present you the project on its like various aspects. I would say, firstly, we'll talk a bit about the, I would say, code project, really looking a bit about on the code, how it is organized, what it does, and then focusing a bit about the main principles, what makes SOFA a bit specific as a simulation engine for mechanics and biomechanics. Then simulation features, I would say regular simulation features provided by SOFA. A word about the community, how the project is governed as well, how it works, how we do like on an everyday basis and over a year, how the project is actually organized. And then a few like info to take home message, I would say, to really get started on SOFA. So all along the presentation, I will possibly show you a bit of SOFA simulations, videos showing also what people are achieving with SOFA. So do not hesitate again to post and ask all the questions you want. So let's get started. So what is SOFA? SOFA, it's an interactive mechanical framework for simulation, and therefore what is inside SOFA, it's algorithms for mainly continuum mechanics. What it means is that SOFA, it's a simulation tool that computes how objects are moving, deforming, possibly interacting one with another, if there is several objects in the simulation, with various like mechanical laws, interaction possible between those objects, which makes SOFA pretty suitable for creating digital twins. And the community of SOFA is using those simulations for mainly, I would say, two kinds of applications. We have digital twins used for medicine, so having this digital health projects where we can use simulation for training, surgical training, preoperative planning, intraoperative guidance. We'll get back to that. And the second application field where SOFA is actually used is robotics, which is for the project a bit newer, I would say a bit more recent. And we use simulation to model robots, obviously, but to also design new robots, test and create new control laws for those robots. You can, for instance, on the bottom right, see some like suction cup robots, which can like capture a box depending on its own weight, and depending on the number of suction cup, you can see the robot will succeed or not to make it up. So why choosing SOFA? Because you might also, I guess, the EuroCC community might be pretty aware of like various commercial or academic software for simulation. So I would say, why SOFA, or what makes SOFA specific? SOFA, it's especially designed for having simulation where you have a lot of interactivity. You can, for instance, see like a simulation which is used within a learning process, where you have, in that case, a reinforcement learning algorithm using SOFA to learn how to control a robot. You can have here interactions of a user that will pull and tear some tissue. Or again, on the top right, you can have a robot and possibly a user learning how to manipulate a robot with this simulation. So the key word of SOFA, I would say, is the interactivity. That's really what is making SOFA specific compared to other solutions. So let's discover a bit the software project on the, I would say, on the code side. It's a code project, it's a software project that arose back in 2006 at INRIA, which is a research institute in France, working on computer science mainly and robotics. And from the very beginning, SOFA started from the collaboration of several research teams that really had the desire to work together and to collaborate in the design of this simulation framework. And again, the SOFA, we like to define it as being an open source reference for interactive and real-time, possibly biomechanical applications. When we open the code of SOFA, for those who are possibly a bit code-oriented, for the geekier among you guys, what is inside SOFA? Mostly C++ code. What is the engine, the code, the language of the code that we're using is C++ under a license which is LGPL 2.1. And what does this license mean? This license means that you can actually download, use SOFA, modify SOFA for your own use, and even make product from and made with SOFA, based on SOFA, without having to pay for SOFA. That's an open source framework. And the idea is always, the philosophy which is behind this LGPL license is really the fact that we aim at motivating the partners, including industrial partners, to make the core, the C++ core of SOFA, continuously improving. However, for everything which is, I would say, key for the business of a company or something that has not been published yet for an academic partner, all that can be implemented into some so-called plugins. Those plugins, it's some kind of separate codes which are apart from SOFA, and therefore they can have the license that the user, the developer wants. It can be an open source plugin, but it can also be some private plugins. This model is called like an open core structure, an open core architecture for the project. And that makes SOFA as well pretty suitable for developing business based on SOFA, because you can develop the key components of your simulation in possibly private plugins if you want to keep it private. And if you want to keep it like open for sharing that with the community, you can also decide to use an open source license if you wish. So it's a C++ code, but in fact, we have Python bindings, meaning that you can use also SOFA using Python scripts. So that's also another, that's the most common way actually to use SOFA through Python scripts. There is a graphical user interface, we'll see that comes also with SOFA. So it's a C++ code, a software project, which works on multi-platform, macOS, Linux, and Windows. And we have, like, as all, I would say, a regular project, documentation that comes with it, an API for developers, an API documentation, and also an open forum for getting support from the community. We'll get back to that as well. And since it's an open source framework, an open source project, we are having the sources of SOFA, which are open sourcely available. For instance, you can find the sources of SOFA right here on GitHub under sofa-framework/SOFA. And here you can find the whole source code of SOFA. And how does it work? This GitHub platform, for those who do not know GitHub yet, it's simply like a way of having contributions. There is like the main branch of SOFA, the main version of SOFA, and people can develop features in their own so-called branch, and they can suggest this new feature back into the core of SOFA. This is called in a pull request. So that's a regular, I would say, contribution process in open source framework. So all that is also described in our contributing doc page. So an open source project with a core of the simulation engine so far, and around it you can have plugins implementing new features, new algorithms implemented by either independent developers, companies, or academic partners. If we look into the source code of SOFA on GitHub, right where we actually were just before, what can we find? A set of folders, a set of files, which are actually pretty organized. There is, if we talk really about the source code, two parts. The SOFA core, the framework, where it describes, somehow the skeleton of a simulation, how it should work. This is called in a software project the API. And on the other hand, all the implementation of models and algorithms, and this will be found in the folder SOFA/component. For each component, for instance, a solver, a mechanical constitutive law, and so on, all those so-called components, they will have an associated example that we can open and run with SOFA. And as I said before, a set of plugins that can be found. We have actually various plugins that can be made available with SOFA. How to get SOFA? Two ways. The most simplest one would be to simply download the binary version of SOFA, where you can go on the SOFA website, which is the www.sofa-framework.org, and you go on the download page. So I can go there with you. It's just here, and you go on the download page, and you will get SOFA. So let's go there. Download. You'll have the various versions of SOFA for the various operating systems. Or if you want to have and build SOFA from the sources, so implement, I would say, compile your own version of SOFA, you can download the sources from GitHub and compile it, and you have the whole documentation available for that. Latest stable version of SOFA is the one from last December, 2024 December, so it's called v24.12. And when you get SOFA, you get an executable. You do not only get some codes, random codes and so on, but you get a graphical user interface that you can use with SOFA. So I'll show you I will show you those tools. So here there is actually two different graphical user interface. That was here on the left-hand side, the old one. For the next release, we're going to release actually a new graphical user interface based on actually more modern libraries, namely one which is called Dear IMGY. So let's take a look at SOFA. So if you download the latest stable version of SOFA, this is the kind of graphical user interface you'll get, where you can actually run the simulation, stop it, and here you will see that there is a set of objects that are here. This is actually what we call in SOFA a scene graph, describing each object and their properties, each object present in the simulation. We'll get back to that. So SOFA, it's a simulation engine, but it has some specificity, and we just actually saw one right now. The first specific feature of SOFA is the fact that when we describe a simulation, we describe it using a so-called scene graph. It's a hierarchy which is organizing the simulation, organizing the objects that we are aiming at simulating. It always starts with a root node. It means the root node starts to describe the simulation. And then you see we have some kind of sub-nodes. This was actually visible here on the left-hand side. You see we have here this sub-node. Here it's describing the object that we see here, the snake. And inside this sub-node, we'll have various objects, components that will describe what? That will describe the mechanics of this object. In that case, we have some topology that we load, so a geometry with its connectivity. We have solvers that we can define. We have mechanical models that we can define, like a linear elasticity on hexaedron, which is here, a mass, and storing here a component storing the degrees of freedom, so-called the mechanical object. So this is how we describe a simulation, and this can be either described using an XML language or using Python. Obviously, Python is, I would say, definitely more modern. Here is, for instance, one example of a Python script used with SOFA. You have this create scene function, and then you can add so-called objects into it, into the simulation, so that you start to describe, for instance, the fact you want to use this kind of solver for the object, this kind of forces, external forces applied to your object, and so on and so forth. So we have this scene graph looking like that here. And if, so here, like I should start like that. If we have here an object like here, the lever, you'll have the root node, and we have one subnode. And inside this subnode, we'll have a set of components describing the mechanics, the properties of the object lever. And if we have another object like the heart here, the beating heart, or any other possibility object, for instance, a surgical tool or a cable or whatever, you would have another subnode itself, including a set of components describing how to simulate and what are the properties to simulate this second object, and so on and so forth. This is this scene graph structure that we follow in SOFA. This is one first specificity of SOFA. The second one, so yeah, that's how it looks here. I'm sorry, that's how it looks here in XML. You will see a node opening, the root node again, containing the time step of the simulation. You can even define the gravity applied on the whole simulation. And as you can notice, one subnode for the object lever and another subnode for the object heart. In Python, it would look pretty similar. The only difference is that you have to define a Python function called create scene, and you define everything that you want to put inside your scene graph, so-called scene graph, basically, in your simulation. Each child node is an object, and you define the properties of this object. The second specificity of SOFA is the fact that we define what happens within one time step using a so-called animation loop. The animation loop is basically the cycle of computation of one time step, as simple as that. It rules and orders the steps to be computed within one time step. When to compute the collision detection if there is some, when to compute the constraint resolution if there is some, when to solve the mechanical system that we are defining as a scene graph. This is the second principle of SOFA. So we use a scene graph. We have always in our graph a tool which is called an animation loop to rule what has to be computed within one time step. And the last principle, and for me it's one of the most important principles of SOFA, it's the fact that we can define for one single object. Here I'm actually using the lever that you find here below the rib cage. We can define for one single object different representation. We can decouple different models, different representations. We can use one specific representation, so one mesh, one topology used for the mechanics to compute the deformation of our model. But we can also use other representations, other meshes, other primitives for the collision detection, for instance, or for the rendering. So I don't know if some of you are guessing why this feature can actually be pretty interesting. But the fact is that by decoupling those different representations, the mechanics, the rendering, and the collision detection, so the primitives that we're going to use for the collision detection, it will help us to optimize, find the best trade-off where the efficiency of the simulation will be maximum while having a maximal accuracy where we desire. If we want to have a very accurate mechanical model, but we are less regarding on the accuracy of the collision. We can use a very fine mesh for the mechanics, while having a coarser mesh for the collision detection, or inversely around. And these mappings, they will make the correspondence between those meshes. It's basically, if we talk a bit about math, it's like having various spaces of representation, and the mappings are a transformation between those spaces. So this is very useful to actually reach the most efficient simulation possible regarding your problem. An example here, what you see in red is actually just a rendering mesh, a surface mesh. It's not the mesh, it's a triangulated mesh, which is not the one used for the mechanics. The one used for the mechanics is the blue mesh that you see now, a tetrahedral mesh, volumetric mesh, a bit coarser, that we use for the mechanics. But the mapping is translating the motion computed on the blue mesh and translating this motion onto the red mesh so that we see a smooth, nice red mesh. So that's the power of the mappings of SOFA. So three main principles: the fact that we work with a scene graph to describe the simulation, and this scene graph can be written in Python. We use an animation loop to rule what happens within one time step, and we have this principle of mappings connecting the possibly various representation within one simulation. Obviously, there is then regular simulation features within SOFA. For instance, what we expect the user to provide us. We expect, as any simulation engine, to get a geometry as input so that we know on what kind of domain we have to compute the mechanics. We are using extensively the finite element method for integrating in space mechanical models, mechanical constitutive laws, forces, and so on. So to compute those models, we need a mesh as input, a space discretization of our objects. Those meshes, they can be volumetric meshes, tetrahedral meshes, that's what we use at the most, but it can be also hexahedral meshes, surface meshes made of triangles, made of quads, or even 1D meshes like beam meshes. So it's a set of segments that we can use to model, for instance, a beam-like structure, or a wire, or a catheter, if we talk about like medical application, or some cable, if we talk about a robotic application. And again, using the mappings, we can couple different topologies, connect different topologies and different representation, as we just noticed before. We can have one mesh for the mechanics, another discretization for the rendering, and another discretization using different primitives for the collision detection. It's a physics engine. We are computing mechanics, and we are looking at how things are evolving, deforming, like getting in contact with each other, colliding, constraining each other. So there is a lot of solid mechanics within SOFA, and you can, for instance, find a set of material laws in SOFA: linear elasticity, small deformation, large deformation, using also co-rotational approaches. Plasticity is implemented on some models. Hyperelasticity is also implemented. You can see here a case of plasticity on the image on the top right. You see like a pneunet finger, which is a classical model of robot, soft robot, an inflatable robot. And you see we are inflating it, but by deforming it, a part of the deformation will be kept as a plastic deformation. You can also define also some viscosity onto it. There is a collision pipeline that comes actually automatically with SOFA, allowing you to detect collision and to define how to respond to a collision when one is detected, when a contact point is detected. A set of integration schemes, implicit, explicit, and semi-implicit too, and linear solvers, iterative solvers, direct solvers with various set of factorization too. So I would say the usual toolbox for solid mechanics and I would say mechanical simulation. So that's for the core features of SOFA. But as I mentioned before, SOFA is a core, and you can also have plugins all around SOFA defined and developed by companies, by research teams, or even maintained by a set of developers which are at the core of SOFA. And here is a very short list of them, but you can find all the various plugins, like we have like some kind of plugin place here where you can find various plugins available. Some you can filter them looking at what are the ones dedicated to robotics, what are the ones coupling SOFA with haptic devices, what are the ones, and it's actually not exhaustive here. So that's a good place to look at. And you have also the list here on the documentation of SOFA in, so it's the, I can go from here from the website of SOFA, I can go on doc here, plugins, and the supported plugin list. It's like the officially supported plugins by the community and by the SOFA consortium. So you see, it goes from plugins that like integrate SOFA within the Unity rendering engine, integrating SOFA within Unreal or Blender, or coupling SOFA with some learning framework, like to develop your own AI-based simulation. You can have rendering tools like rendering plugins that allows to mimic X-ray imaging, ultrasound imaging too, that you can find just nearby, and a various set of plugins for instance, soft robotics and numerical methods too. So do not hesitate to just visit the website and check out for the various additional features brought by all those plugins. As I mentioned before, we have two main application fields that we target with SOFA. The one I would say, the historical one, is application in medicine. We used it, as I said, in the introduction of the presentation. We can use SOFA, and people actually use SOFA for medical training, where the simulation can be used really as a tool of rehearsing, learning surgical gestures, avoiding obviously the first gesture on a patient. I mentioned that we have a set of plugins that allows to couple the simulation, virtual simulation, with haptic devices so that you can get force feedback from your simulation. We are having collaboration with super cool, actually, haptic devices company like Robotics or Follow Haptics company, which are providing, I would say, really state-of-the-art haptics, pretty nice to couple with simulations. So you can use also simulation to use all this knowledge of biomechanics to predict the outcome of a surgery, so that you can optimize the strategy before the operation, defining the strategy, the trajectory, the entry point, and also optimize, possibly, the devices themselves, like to replace a valve, or to design a catheter, or to design, I would say, a plier that would be patient-specific. So that's all this prediction and patient-specific pre-operative planning is something that can be achieved also with simulation. The two images here are actually provided by some research team of the community, which are INRIA research teams, by the way. And the last, which is more, I would say, a long-term objective, is also to use simulation to guide surgeon during the surgery, where you could provide additional information while the surgery is being performed, adding visual information, help navigating, keeping the possibly target inside for the surgeon, and all that on the surgical screens that the surgeons already have in the operating room. Second application field, soft robotics. Soft robotics, as I said also in the introduction, we can use simulation to model deformable robots, but we can also use simulation to model a robot which is partially deformable, or a robot that will interact with a deformable environment. And we can use simulation to design new generations of robots, like those deformable robots, as I said before. Those ones, we call them the soft robots, because they can be made of silicones or even like biosourced materials that can be inflated, actuated by cables, actuated through fluidics actuations. So there is really various kind of actuations and robot design that you can achieve. And simulation can really be used, as you can see here it's a work done by colleagues at McGill in Canada, where they are actually using SOFA to model their crawling robot. And in that case, it's actually a link with the third bullet point. They are learning here, they learned to a neural network, they trained a neural network with simulation. And the objective of the neural network was to find the optimal locations of the legs, the red legs of this robot. The legs could be placed anywhere on the central part of the robot. And the robot so the neural network had to run simulation and find an optimal strategy, which is the one we see right now. The optimal strategy to crawl as fast as possible in a certain amount of time. So this simulation, again, can here be used really as helping closing the simulation to reality, so what we call the sim to real gap, the difference between simulation, virtual world, and the real world, the experiment that we have here. So that's also a strong activity in the community to work on those sim to real simulation that we lead, especially in soft robotics. And for that, in soft robotics, as you can guess, we have a set of plugins that comes for some of them automatically with SOFA when you download the binary versions of SOFA, providing pneumatic actuators, fluidic actuators, cable actuators. There is even on the bottom right what you see here. It's a simulation from colleagues at ETH in Zurich, in Switzerland, where they are actually using SOFA to learn how to control a catheter which has an electromagnetic tip. And with electromagnets, they are actually learning to control and automatically navigating this catheter with as you might see here at the tip of the catheter, a black tip. This black tip can be oriented through the magnetic field. And obviously, what comes with those plugins also is plugins to improve performances with model order reduction, multi-threading, GPU computing, and people like to couple a lot simulation with reinforcement learning or neural network, as I already mentioned before. I would like to stress the fact that we are also widely supported by a French initiative where we benefit, we have been selected, SOFA has been selected as the simulation framework to model the digital twins of all the robots designed by French robotic labs. So that's, I would say, the official framework, the official platform for designing robots when there is deformation that comes into the simulation. A word about the community now and how the project is actually governed, how it works. Because it's an open source framework, I don't know if everyone is well aware of how regular large open source projects work, I don't know, Eclipse or Mozilla or this kind of big foundation, but you need to have some kind of leadership of your project. And for the last 18 years of development of SOFA, obviously the community started to grow. We now have a set of daily developers working with a SOFA-based software. We have regular users. We have, as you can notice here, a set of monthly downloads, and same for the clones of the sources. And to give you some numbers about SOFA, which is definitely here a proof that open source framework can be an innovation catalyst, as I put in the title of the presentation. It's the fact that since its creation, since its kickoff back in 2006, we had actually 12 companies created around SOFA worldwide. I would say 70% of them were actually French companies due to the close relationship, but not only. For instance, one of our closest partners today is a South Korean company using SOFA for developing their medical robot, helping to automatically insert and guide catheters within the human anatomy, within actually endovascular structures, our blood vessels. The community of SOFA, it's still mostly academic, as you can notice. It's mostly research labs, but it tends actually to change. We have more and more industrial partners that are actually joining or getting closer to the project, as you can notice. So LN Robotics is the South Korean companies I was mentioning before. Insimo is one of our spin-off that we have in France. Robotics, which is another like French company, which is one of the partners of SOFA, but which is not a spin-off of the project. Dassault, a French international group. Essilor, and it's just like it's obviously not an exhaustive list of the industrial partners. Academic partners, again, not exhaustive, but a set of partners that we are working with, like on a, I would not say on a basis, but like super regularly and continuously. That's what matters to us, and all over the world. So if you want to join the team, you are most welcome to join us and work with us. As a reminder, if you have any question, do not hesitate to drop them in the Q&A area, or if you don't find it, you can put it in the chat. We also have an eye on the chat, but really do not hesitate to post and to ask all the questions you want about the project. As we said before, as soon as you reach a certain, I would say, size of project, you need a bit of coordination. And that's what actually a regular open source project are facing. We need to coordinate and to define a bit what is going on, structure the development, structure the community, and that's what we actually do with the open source SOFA consortium. The SOFA consortium is actually a set of engineers funded by our partners, collaborators, and together, we actually work on the coordination of the development. It means that we make sure that there is actually not two different teams, two companies, or even more, developing the same technologies without collaborating, or at least without knowing each other. The purpose of SOFA is also to create a network of skills, of knowledge, and to make sure that, also of, I would say, profiles, and to be able to collaborate, to exchange students, engineers, and to build like better products also at the end of the day. The SOFA consortium engineers are also working on the industrialization and the maintenance, obviously, of the project. Animation and support of the community, and structuring the ecosystem. An example of what is structuring the ecosystem, it's not only buzzwords. It's, for instance, if you are looking for specific partners with specific skills in simulation, that's our role, especially as third party in the community, to put you in contact with anyone you want, and I would say the best partner possible within the SOFA community. So here are the 5 members of the consortium: INRIA, the Research Institute, LN Robotics, a company developing their their robot guiding automatically endovascular catheters within the blood vessels. Insimo, which is developing simulations for training, and not only, so medical simulation for training. Caranx, which is a robotic company in healthcare, and the University of Clermont, which is developing stent simulation with SOFA, so again, a medical application. And how it works? Who decides how it works? It's actually a well-defined governance in SOFA, where we have a set of partners participating in the executive committee. And this decides actually the priorities of the consortium engineers. What has to be targeted at first, what is the most urgent for the partners? Communication policy, obviously, changes in contracts and so on. And we have a technical committee which gathers twice a year and that will define and discuss the roadmap, the technical roadmap to define in which direction the project should go and give visibility and readability also from the outside of the project. You can therefore, when you go on the SOFA website again, you can notice that in Consortium, you have a web page for roadmap defining the official roadmap of SOFA. You will see here the topics on which we are actually strongly focusing for the next 6 months. This consortium has also the responsibility of development process, I would say structuring them, making sure that those development processes are respected to ensure robustness, having contribution rules that are actually explicit, a reviewing process, which is explicit because not anyone can push something directly into SOFA. It goes through a review process, a validation process, a continuous integration that will test on various aspects, regression, unit, feature tests, the changes, so that we make sure that SOFA is actually not breaking when we integrate a new feature in SOFA. And this way, we regularly release new versions of SOFA, like I said before. The latest one is the 24.12 for the release of SOFA of last December, and the next one will be the V25.06 for the next release that will be made in June. So we usually do that every December, June, and so on and so forth. The purpose of all that is definitely to also improve constantly the industrialization, like remove bugs, improve stability, improve the code quality, very important, improve the documentation quality, and tracking bugs. So we get close to the end here. So again, do not hesitate to ask all the questions you want in the Q&A area or in the chat. How to get started with SOFA? So first, I hope I convinced you that why choosing SOFA? SOFA is really focusing on these interactivity aspects. On the top right example, you can see what? You can see a jelly cube or like a jelly rectangle, which is doing what? Which is deformable and in which we can insert a needle and this needle will deform. It's a deformable needle. The needle deforms itself and can also deform the gel. On the middle one, you can have here an augmented reality view on a lever, targeting automatic guidance within operating rooms. We have also like startup projects on that. And the bottom right, it's actually the result of a research paper that was aiming at displaying the power of anisotropic foam used for soft robots. And in that case, it was allowing two, I would say, pretty simple shaped robots, but that were reaching pretty complex motion to actually solve here a maze. So really, SOFA is obviously like we aim at making the architecture, the code as modular as possible with the open core structure. The design of a simulation using Python, and we are even working on additional, I would say, Python interfaces for users to make the design of a scene as efficient, as easy, as fast as possible to have like quick prototyping of simulations. And really always aiming at having interactive mechanical simulations. So learning SOFA, actually there is several ways. First, you can like get to learn SOFA alone on your own, but I think there would be more efficient ways to do that. You can take courses through actually the teaching program, the learning program that is developed at INRIA. It's a program to learn, get courses on open source framework that are developed at INRIA, including SOFA, but not only, including also like AI libraries like scikit-learn or others. You can get courses for your own teams or join existing courses. You can have access on YouTube for SOFA on free online introduction course. And you can get support anytime. You have the documentation, as we said before. Just to show you again, on the SOFA website, you cannot miss it. It's just right below the download button, you have the doc button, and you end up on the SOFA documentation. You have a forum on GitHub. Again, the GitHub website of SOFA. Here, discussions. That's the forum of SOFA where everybody is posting daily questions on SOFA. And last but not least, it's more like for chatting. You can also join the team on Discord where developers are actually chatting not only about code, but so that's a good way to get to be known and to know also the developer community of SOFA. All this information is all gathered on the SOFA website, on SOFA framework, on community, get involved, and there you will find all the ways to get involved at your own level and at your own speed, at your own chosen speed. So my whole take-home message would be just let's collaborate, let's work together if you want. If you are like an academic or willing to work with an academic partner, there is like we can set up a joint PhD thesis called in France it's called CIFRE, but there is mechanism to fund like joint research work, bilateral partnership, or even jointly write EU project proposals. You can get partners which are industrial partners, can get in touch with companies of the community, to get consulting, technical support, tailored development, or even co-develop together products. And last but not least, obviously, once you are working with SOFA, you can get closer to SOFA and become a consortium member. If you will be, so I see that there is question already, so thank you, Maxime, for all those questions. If for the others, you have been too shy, or it's the first time possibly that you are discovering SOFA and it's been possibly too many information at a glance, no problem. There is other events where we can meet. Everything is actually listed on the SOFA website too. Events, click here directly on events. You have the full agenda, 2025 agenda of SOFA, and you can find our various events where guys of the community will be present. The main event is definitely the SOFA week. Every year in November, this year it will be in France, in Lille, from the 24th to the 28th, of November. And the main day is definitely the 25th, because it's the day of conference where there will be talks about SOFA, demos using SOFA from academic, industrial partners. There is like PhD students looking for new jobs. There is companies looking for students. So it's also a very good place to network with the community. So I'd like to end by thanking you all for joining this session of today. I'd like to thank as well EuroCC for allowing me to present SOFA at this occasion. If you are watching this presentation online, it's never too late just to contact us per email, even long after this session. Thank you all for your attention, and I'll take all the questions, and I will start with yours, Maxime. So do not hesitate for the others to again take all the questions you want. So the first question is how is Python actually installed? Is it possible to use global Python through the Conda or Anaconda environment? So the question is yes to both. You can either install SOFA through Conda, which is an installer for those who do not know Conda, installer made for a Python project. You can actually see that here on the download page of SOFA. We now added a Conda installation area where you can get all the information on how to install SOFA using Conda, which is a lot like all the Python compatibility issues that you can face possibly if you have different versions of Python on your own machine. How to define a completely rigid object that moves along a certain trajectory. So that's actually very advanced and specific questions, but I'll take them anyway. If there is more generic question, guys, please feel free to post them. It would be, again, a pleasure to answer them. So how to define a completely rigid object that moves along a certain trajectory? Insofar, we would define actually the object as, if we look a bit at a script, like here, the object would be a rigid object. So we specify the template as being rigid. That will define the fact that we want this object to be a rigid body. And insofar, you will have a set of, let me, if I get the time to go here in components and constraint, we have a set of, for instance, projective constraints. And here you can define affine movements to define like a projected affine movements, a projected affine trajectory to simulate that on your object. That's one way of doing it. There is actually a lot of ways to define that kind of motion. I'll take the one of Gonzalo. Is tensor visualization available in SOFA? So I guess you mean like strain tensor and stress tensor visualization. So if it's not the case, please correct me anytime in the chat or in the Q&A area. But if you are referring to the stress and strain tensors, you can actually visualize them in SOFA. So let me take, for instance, an example here. I will open one of the examples of SOFA. Right here, component. I will take, a case of solid mechanics. And I will take here a linear elastic model implemented over tetrahedron. And here you see a set of beams on which we can actually visualize the stress tensor associated to those different small deformation, large deformation, polar and SVD decomposition for the co-rotational approaches. And you see the associated stress distribution according to the various methods. So you will see immediately here the small deformation, right? The small displacement, sorry, hypothesis, where you see the beam which is expanding due to the approximation on the strain tensor, linearization on the strain tensor. So that's what you have here, and how we can actually just how it works. If I check here let's take the small deformation. Sorry, here I'm opening here the component which is the tetrahedron fem force field implementing the linear elasticity on tetrahedron. And you will see here for visualization, you have a set of options, including show the von Mises stress per node color map. And all that obviously can be accessed in Python. So all this information here, I just opened it in the graphical user interface, but you can actually work with that through Python. I could like give you a set of additional examples based on Python if you'd like. So the next one, yeah, thanks a lot, Julia, for your feedback here. You mentioned various mechanical models. Does implementation of mechanical models using, I'm sorry, I lost the question here. Okay, there we are. Can I struggle to actually see it. I'll try to make it bigger, like that. Julien, I'm sorry, I cannot. I'm struggling in the. Yeah, I'll get back here. Okay. You mentioned various mechanical models. Does implementation of mechanical models using specific strain-stress relationship or strain energy density formulation are available? It's actually so we have a set of various models. If your question is, can we manually define, let's say, a strong form or an energy, strain energy form of your material law? Not actually, we have a plugin which is doing that, but it's, I would say, in an ongoing work, and we have a project which is aiming at integrating that back into SOFA so that you could, in a strong form of your equation, or possibly an explicit description of your strain energy density, to formulate that and provide that to SOFA, and so that to have an automatic differentiation of your energy and provide an automatic generation of your mechanical model. So automatic generation of models based on the strain energy density formulation. It does not exist yet in the core of SOFA, but it's an ongoing project. So I hope it answers your point. I'll take back the question of Maxime. If I want to integrate an external controlled influence into the simulation, can this be done through animation loop? For example, at a certain moment in time, set a gradient or an external force that would change over time. So for that, what you are asking, Maxime, is basically how can I somehow interact with the simulation once it runs? So I'll get back on the slide here and just there. Yeah, perfect. So I will here. Yeah, this is the good one. I will show you an example of what can be done with Python, working with SOFA and Python. Sorry, I will open that straight away. SOFA training scenes. I will show you two examples. So this is one first example. It's a very basic example. You see, we have a rigid frame located in 0, 0, 0 in the world coordinates. And I will run the simulation. If we open the node corresponding to this object, rigid particle, we see that it has a mass, okay, and it has a constant force. But for the moment, the force applied to this particle is equal to 0. In Python, what we can actually do is with anything, but here what I define in the underlying Python script is that using a keyboard event, I can change the force applied to my object. Here, by pressing plus, minus, and so on of my keyboard, I am dynamically changing the velocity of my particle. So here I just restarted the simulation. So I can, therefore, through Python, access information at the beginning, at the end of the simulation, but also during the simulation. And not only can I access information while the simulation is running, so I will again change the velocity. Here you see by pressing the plus key, I added some forces in X and Y to my particle. But not only can I do that, but I can as well, by here, I'm pressing this time the A key, and you see, I am adding new particles, which means what? So I'm stopping the simulation here, which is meaning what? That we can even create or destroy, delete objects inside the simulation while the simulation is running. So you see, with Python, you access a level of interactivity which is pretty high compared to what you can usually do in other languages like XML or a basic Python script. Here, Python can also allow you to access really data of the simulation. So you can access, as it has been asked before, stress and strain tensor. You can access velocity information, any information from your simulation. Okay. So I hope it answers also your question, Maxime. Christina, I'm trying to change a bit for the people who are asking the questions, or a question of Christina. Hello, and thanks for and thanks for the webinar. I was wondering, may I transfer the Python files containing the simulation in Unity? If yes, how? Through the plugin. Yeah. So indeed, so working with Python script is now possible also in Unity, if I'm correct. But this would be indeed definitely done if we get back to the associated slide here. using the Sofa Unity 3D full integration plugin, which is developed actually by a company, which is providing this open source plugin, and that's the Infinitec 3D plugin company. Sorry, that's also a video of the Infinitec 3D company that you can see here on the top right. So it's again a surgery on a liver. So I hope it answers the question. I'll take another one, and do not hesitate to stop me, Guillaume or Marie. Do not hesitate to stop me if we reach the end of the session. Maxime, so is there any ready-made library with predefined biological materials? In fact, biological materials can already be modeled using existing materials of SOFA. The question is more, which parameters do you set to those tissues? So with values to set to model a brain tissue, a muscle tissue, a liver tissue, a fatty tissue, and so on. So we actually plan, we are within the development of application-specific Python libraries, and possibly this would include, I would say, predefinition of materials. We are aiming at doing that firstly for soft robotics, but we possibly will do the same for biomedical application too. So possibly adding some predefined indeed biological materials. So as is, we don't have like an option in SOFA saying I want to have a liver, the classical liver property. But with the existing materials constitutive laws available in SOFA, you can already model liver properties as it is usually done in any other simulations. Just a question of defining the right parameters, but this can be found in the available literature too. Have you ever noticed anyone modifying 3D printed objects in SOFA, taking into account different methods of filling patterns? So yeah, that's a good question too. Thanks for all the questions. It's actually pretty interesting. There have been some work. Actually, I showed you one of the work which is doing that. I think it was pretty much at the beginning. Let me find the video again. It was when I was talking about soft robotics. Okay, it's right here. Where is that? Here. Yeah, here. You see on the bottom right, the foam is an anisotropic foam, so an oriented foam. And this was actually 3D printed by some research team working on 3D printed foams. And the foam itself has been optimized through simulation. So we use simulation to optimize the design of the foam, so of the 3D printed foam itself. So I hope it answers the question. Is it possible to test and model auxetic materials? So that's a good question. So that's something which is we are looking at that currently. Having if it's just setting a negative point. So I'm not myself very well aware of auxetic materials. Is that like nitinols and similar materials, or because if it is, it's actually a current topic of interest, and else having negative Poisson ratio would be feasible too. But yeah, we did not have like extensive work on that topic, Maxime. But we could do not hesitate to get in touch. We could I would happily like take a look with you about that and see how we can go forward with it. I think I got them all. I got most of your questions. If it's not the case, please poke me in the chat. Let me know that I forgot one of yours. And otherwise, thanks a lot for all the questions. There were actually some of them pretty like top level questions. Thank you for that. If I want just to say one last word, it would be just keep in mind for SOFA, this free and open event that will be late 2025, 25th of November. It's easy, 25th of November 2025. We can meet in the north of France, and you'll see there would be the entire community of SOFA assisting to the event, making demos, making presentations, and networking on mostly one day, but it goes with a training day on the Monday, the conference day on the Tuesday, and the technical committee on the 3 last days of the week. So definitely I would say the best moment actually to network. Thanks a lot, everyone, for the attention. Thanks a lot for all the questions. It was very nice to add so many. And yeah, I hope to get in touch anytime. You can email us anytime at consortium@sofaframework.org. Thanks a lot for the organization, for the EuroCC board. And yeah, see you soon. Bye, everyone.